So what you're looking at now, we've gone back to chasing the RBC signal, which mutes the audio. Now the signal generator is on and the receiver is receiving, but there's no audio coming out. And what you're looking at here is the chip that the RBC signal goes into. But this transistor, which is a modification, has been put on with a piece of sticky tape. I don't know if you can see the sticky tape there. Now if I lift that sticky tape, listen to what happens. You hear that? Lift the tape and the signal comes up and it goes down immediately after. And it doesn't seem to be a dry joint, it does seem to be that tape. There you go. So we're going to remodify that. I don't know what the transistor's doing, but we'll try and trim that piece of tape and see if that particular logic fault goes, and then we can look at the Vox operation and the braking. We've already given up on the CW board, that's definitely faulty. So we've emailed Kenwood, but there's not much hope with a radio of this age. So catch you later. So I've removed the tape and the signal generator is on and there's no audio. All we have to do, in fact, is just touch one of those pins and the audio comes up and then it fades off again. We touch the other one and it fades off. 12 and 13 are the inputs to the NAND gate and 11 is the output of the NAND gate. And if we go and look at pin 11, that's running at 0.3 of a volt. Sorry, it's 3.1 volts. So it's not a true logic high. But this is a surface mount device and I can't see any printed circuit going to any of these pins, and I can't find that gate, 11, 12, 13 on the schematic diagram. Now normal design practice would be that any unused gates you strap to ground, so you take these to ground and then it doesn't float, doesn't affect what's happening inside the chip. Just a touch and it's on, and another touch and it's on. So I'm going to have to take the board out. I'm probably going to change the chip anyway, but if those gates really aren't used and there doesn't seem to be any printed circuit going to them, then I will strap the two inputs to ground, and that should stop that reoccurring. Would be interesting to do it on the chip that's in there, but if I'm going to take the whole board out I might as well change the chip anyway. So again, we'll continue this a little bit later on. Okay, a little bit more on this Cmos chip. I haven't got one in stock, so I'm going to have to wait. But you remember in the last little segment, whenever we touched any of the gates, let me just see if I can touch one, the sound comes up, you can hear it there, and then that fades away and it's gone. And the voltage on the pins is not correct, not for Cmos anyway, and I'll explain a bit about TTL versus Cmos. They work in the same way, they just have different voltage levels. If I go on to the output of the NAND gate, which is that pin there, I'm using the oscilloscope lead, and then on the oscilloscope, see if I can focus it, yes, you can see, no, it's going the wrong way, but you can see that that actual gate is oscillating at what is it, just over 100 kilohertz. Now as far as I can tell, there's no track going to any of that side, which I mentioned is really bad design practice. You never leave gates floating because this sort of thing can happen. Yeah, and if I go back to the voltmeter, I'll just confirm the voltage that we're seeing there in that state. So if we go on to, try and get another focus. So if we go on to the output, things are getting in the way. So that's the output of the inverting gate, and that is 1.5 volts roughly, which is neither a high or a low in Cmos. The Cmos has a percentage. So we'll go on one of the gates. There's a sound coming back, and the voltage there is 0.06, and on the other gate it's the same, 0.06, and the output gate now is at 15 volts, and the sound's just gone off. So that they're in the state when the sound was present, they had valid voltage levels, but now the outputs remained at 15, but the input's gone to 0.7, 0.8. So, you know, it's certainly not acting as a piece of logic. The gate number I can't find on the schematic at all in the control section schematic, and I can't see any tracks going to it, either from underneath or on top. Now it may be linked to other parts of it, I don't know, it's difficult to say, but it's certainly not documented, and until I get it off I won't actually know. But it's not surprising to me that it's oscillating and is very sensitive to touch, because it's running at a self-resonance which you destroy by putting a probe or a test meter lead on it. So that's what's going on there. So I'm going to move on now and set up to see if I can also track down why there's no Vox operation or breaking from CW. But I can't put the CW board back because we know that's faulty. So just stay with us, and we'll add to this segment later on. I mentioned I would do a little more about Cmos and TTL. So when I was a sprog, I lived in the time, or worked in the time, when we were casting valves away and going into semiconductor technology, and the first of the logic that came out was TTL, or transistor logic, and everybody had these 3 data books which actually detail by number every piece of TTL. It gives you the diagram of what's inside the chip, the pinout, and the logic states. And you know, everybody who was into servicing or designing had these 3 handbooks. And by way of example, if I look at the 4011, which is the gate we're having problems with in the radio set, then there you can see, here we go. So this is a 4011, that's what's inside of it, 4 NAND gates, and the pinout of those, a brief description. Then there's a logic table, so the inputs are A and B, and the output is called Y, and the L and H are the logic levels on the input, and an X means it doesn't matter, it doesn't care. So you can see from this table that a low on any input will give you a high at the output, but 2 highs on the input, A and B, will give you a low on the output, and that's because it's a NAND gate, it's inverting, so 2 highs will give you a low. If it were an AND gate, 2 highs would give you a high, and you get a range of sort of voltages it will work over, etc. So these little handbooks are quite handy. And then came Cmos. Let me see if I can focus this. There we go. Basically TTL was always operated at 5 volts, and if you operated it at higher than 5 volts you tended to damage it. It was also quite current greedy, and along came later on Cmos versions of TTL. But for this explanation we'll stick with the basics. So transistor logic was 5 volts maximum operating, and as such the valid noughts and ones inputs were predetermined. So a low input would be any input between 0 volts and 0.8 volts, and a high output would be any voltage from 2.7 to 5 volts. And the high doesn't have to be an output, it could be an input as well. So if you put your meter on and you found it was hovering at say 0.9 of a volt, then it could be determined by the chip not to be a valid low. It could be a high, it could be anything, which is why you would normally tie the gate down. Now looking at the CMOS is different, because CMOS will operate at much higher voltages, and also more modern technology has taken us down to 3.3 volt CMOS, and that's used, it's quite popular with the microcontrollers such as Raspberry Pi, etc. And because it has a wide range of operating voltages, then the valid logic states are given as a percentage or a fraction of the operating voltage, which is called VCC. So typically a 0 would be any voltage that lays between 0 and 1/3 of VCC, and a valid high output would be any voltage that's 2/3 VCC to the actual VCC level itself. So that's how you know you've got valid signals, or signals which are acceptable on logic chips. Now the inverting gate we saw had an output of 3 volts operating from 15. So that's obviously not a valid logic high, and the gates were also around about 2 volts until you put your probe on them, and then they went low, and you know, the gate stopped oscillating. The reason that the gates oscillate is if you get sort of inverting coupling between the output and the input, oscillation will take place, and they will oscillate at whatever random frequency the L and C components would be present, you know, and that would be stray C, stray capacitance, and whatever L it can conjure up from the printed circuit. So it's not an in-depth lesson, but I think if you get into it you'll find that logic design is very interesting indeed, and I'm sure you will find it helpful. Those data books, which are just called the Cmos and TTL pocket books, they were actually published in Germany, I believe, but brought to the UK, which is where I come from. Yeah, printed in Germany, but available from Romford in Essex, and all the popular component suppliers used to sell them. So very useful thing to buy if you're into repairs. So let's move on now and look at the other problems in the radio set. Okay, so I'm still waiting for parts to come, but I decided to take out the inverting NAND gate IC6 which controls the muting of the receiver. And as you can see on the left hand side, the two gates on the left hand side have no printed circuit track going to them at all, which means that they are floating, and that's the reason with the gate was oscillating. So when I put this chip back, I will be shorting those gates out to ground to prevent that state happening. But interestingly, the gate next to it also appears to have no tracks going to one side, and as I said, that's not acceptable design practice. I'm surprised that a company like Kenwood would do this, because if you don't tie the gates down, they can adopt any voltage that's floating around and cause problems. So we will be attending to that. So next I'm going to, when the parts come, replace those chips, put the control board back and check that the receiver is then functioning properly, and then see what is causing the keying problems on Vox and CW braking, which may be on one of those daughter boards, one of these daughter boards, which I'll probably do some testing on while I've got the control board out. We'll be back with you soon. Right, well, we're at the end of part 2. I've replaced the chip. I've shorted the redundant gates down to ground so they don't float. And now when we go to transmit, if I can find the button. Oh, not found it. The receive comes back on immediately. So what's left to do now is work on the other things that are not working. The full braking from CW and the Vox, which may again be on that board. I just got to tidy up the some of these modifications that have been done. I have found a document with some of them in. I don't know what the rest are yet, but we're getting there. So that's it. I'll terminate this particular segment, put it all together as part 2, and then we'll start on the rest of what's wrong.